Welcome back. Let's keep thinking about the questions that a researcher or an engineer or whatever will need to be asking him himself or herself before picking a model. And we're up to question 5 that you need to be asking, and this is about resources. Do I actually have the resources it's going to take to run this model? Now, in the case of a mathematical model, we're talking about computer power. A simple model like the log wind profile or the Jensen model or something like that, I mean, they're just an equation. That's no big deal. But if we're talking about like a full 3D fluid mechanics model, numerical weather prediction, the kind of thing you're going to learn about in the next lecture, well, these kind of things take enormous amounts of computer time. Days of computer time to run their calculations, and they produce literally terabytes of output data. I've certainly been involved in lots of research projects over the years with my colleagues overseas, where suddenly one fine day I just have to get, like they'll run the model over there in Germany or something like that, and then they just have to mail me a hard drive with a few terabytes of the output on it, because it would frankly take too long to try to download it over the internet or something like that. These models produce enormous amounts of data. Maybe the wind speed at all these different locations on a map at many different heights at all these different times, plus the temperature, plus the pressure, plus the humidity, plus the cloud cover, plus whatever else the model is predicting. It's just an enormous amount of data. I love the analogy of it's like drinking from a fire hose. I mean, these models can produce data as fast as the hard drive can fill up. And you need all that output, but boy, it's just an enormous amount of data. To actually run a model on site, it's not as hard as it used to be. A reasonably powerful computer can run even a fairly sophisticated model in, certainly not more than hours to days to simulate something. And, in a research context or something like that, that doesn't seem like so bad. But boy, are you going to have a lot of output to work with. You're going to need a lot of disk space and a lot of ability to process all this stuff. Do you actually have the physical resources it's going to take to drink from that fire hose? All right, number 6. Speaking of all that output that you're going to be getting, do you actually understand what all of it means? I mean, the output can be, of these very sophisticated models, can be shockingly detailed. And it can look really accurate with lots of significant digits. And it can be displayed very beautifully. But you have to know what it actually means. A common numerical weather prediction model that is used in the context of like energy and so on is the so-called WRF model. WRF is an acronym for Weather Analysis and Forecasting. No, sorry, I forget exactly what it stands for. Weather Research and Forecasting, I think is what WRF stands for. Anyway, it's just the WRF model. Anyway, I mean, the WRF model, every time it writes to the hard drive to tell you what's happening at that time in the model, like, we're simulating, maybe every 5 minutes of time you want to know what the winds are now or whatever, man, it writes out all kinds of data describing, both horizontally and vertically the maps and profiles of the wind and the humidity and the pressure and the density and cloud fraction and amount of aerosols in the atmosphere and all kinds of information about radiation up and down in the atmosphere and so on. Makes enormous amounts of data. Do you actually know what all of that stuff means? I mean, look at how easy it is to be seduced. Here's the output of some kind of model of wind going over a wind turbine. Man, doesn't that look beautiful? I mean, I don't know exactly what we have here, but it seems to be some kind of streamlines of the flow. And I don't know exactly what the color is. Maybe that's pressure or maybe that's speed or something as the wind goes over those turbines. Man, isn't that lovely? If I made that plot, I'd be immediately thinking, man, I gotta get that sucker into a publication. That's just a beautiful plot. But what is that thing? I mean, I'm not even sure I believe by looking at this here that wind turbine is spinning in this diagram. Versus the blades are actually holding still and the wind is flowing over them. I think the wind would be a lot more turbulent if it were actually turning. Come to think of it, I wonder what kind of weird conditions this is under. That flow is really laminar. And for that matter, I wonder if this is instantaneous, or maybe this is averaged over, like that was at one particular moment in the model, that's what the wind looked like. Or I wonder if that's maybe like average, like over an hour, that's what the wind flowing over that turbine averaged out to. Man, it's a seductive looking figure. I'd sure love to have that as the cover of my textbook. But I don't know what that means. I would have to have a much more specific knowledge of what this means before I could do anything with it. Same with like, oh my goodness, now here is it. Oh, this is something. I mean, this is another model of flow coming off of a turbine, and I'm not, well, I don't know for sure what the colored areas here are, but there's something, and they're clearly going downwind from the turbine itself, and, well, this looks more likely to be instantaneous than average. That looks like a snapshot of something, maybe wind speed, maybe dense, oh, I wonder what conditions. It doesn't seem to really be spreading out that much. It doesn't seem like it's following exactly an N.O. Jensen. Do you see what I'm talking about here? It was so easy to look at this and go, gosh, that's a beautiful picture. And look at all the details and all the structure in there and the wind going over those turbines. And yeah, but we still don't actually know anything. Without actually having specialized knowledge of what the output is and what the output means, the models are going to be very tempting and very misleading. Oh, look at this beautiful wind farm. Oh, I even have more information here where we can actually see that the wind speeds, oh, in the darker blues there, according to that key, are winds that have slowed down. And I wonder what we're seeing here. Like, I wonder if that's winds at a particular height or at a particular time in the model. And it looks pretty turbulent. I wonder if this is daytime or nighttime conditions. See all the kinds of questions you would need to know the answers to before you could be making decisions about whether this output is the kind of thing you're looking for? It's so easy to run a model. Well, that's not really true. It's not that easy. But it is easier than knowing if it was the right thing to do and knowing what to make of the output. While we're on that idea, by the way, our final question is, what do I understand about the output's accuracy? I mean, every model is going to make output, but that doesn't mean it's right. There's two different important ways in which the output of the model can have errors in it. And that's actually an important aside that your book for some reason kicks over to section 8.5. You have to like leave this section of the book and move over to section 8.5 and then come back. But basically there's two kinds of errors that can get into your output. One is based on their input dependent errors. They're errors based on problems with your input. And there are inherent model errors. These input-dependent errors are kind of easier to make sense of. Remember that the input for any kind of mathematical model is going to be in the form of numerical data about observations and the state of the system, measurements of the wind, the temperature, the pressure, and the roughness, and the terrain, and so on. And all observations have different kinds of errors. Problems of precision, problems of accuracy, etc. The kind of things we talked about way back when we talked about instruments and so on. Well, I don't think it's a huge surprise that if your measurements aren't good, there's no way your model could produce a correct forecast. You can actually go to box 23 in this chapter for more information about these input-dependent errors, and there they'll drop the clever phrase garbage in, garbage out, right? If the input to your equations is garbage, what's coming out is going to be garbage. There's no way you can get the correct answer. The question is, how good is good enough? How do you even know if your equations need terribly accurate input information? Is knowing your winds to within 1/10 of a meter per second enough? Is knowing your winds to 1/100th of a meter per second accurate enough? How do you even know? Again, we'll get to that when we start talking about chaos in the next lecture. The other kind of errors that we're talking about are the inherent model errors. I mean, by their very nature, the whole point of models was that they were inherently imperfect because they were made to be simpler than the real system. We will always be neglecting certain impacts or making certain assumptions about the environment or whatever like that that may or may not be all that great. And the model will only be as good as how well the real situation matches those assumptions. And so, please go and see figure 8.3 and the discussion in the text that gives an example of this. But the idea that, our log wind profile is a lovely model of the atmosphere, but only under the extent to which we can make the assumption that that layer of the atmosphere is statically neutral and whatever all the other assumptions were that went into the derivation of the log wind profile. And the same is going to be true of any model. And there are intrinsically assumptions that we have made, simplifications that we have made, that are introducing errors. we've run our model. We're working on our workflow here. We took our input, we put it into our model, be that as little as an equation or a statistical relationship, or as much as a full-blown 3D fluid mechanics numerical weather prediction model. Now we've got output. And output itself can be lots of different things. It could be as little as like a single value, you know, like our model of the wake wind speed from the Jensen model, where we just found out what the wind speed would be. Or it might be gigabytes of three-dimensional grids of temperature, wind speed, pressure, humidity, etc. from like a full-blown numerical weather prediction model. Our output could also be graphics. Lots of models have a step in their execution in which they produce they produce graphical output, so that you can then look at the output and make decisions about what happened in that model. That output can be instantaneous, like that is the value at, you wanted a forecast of what the winds were going to be doing 1 hour from now. That is the value at exactly, 3,600 seconds from now. Or that might be like time average. That might be the average of the values from 1 hour to 1 hour and 10 minutes from now. Okay, it's a 10-minute average. Those might be the anomalies, the ways in which the wind at that time were different from the average wind at that time, during that day or whatever. Those might be think about the Jensen model. The value that we got was not the average wind, was not the wind speed at a point. It was the average wind speed, recognizing that there were turbulent flow inside there. The wind speed that we got was kind of an area average. It was not at a particular point. Any model is going to have all these and more issues, and making sense of what is the model's output actually telling you, again, is in many ways more complicated than actually running the model itself. So just to review, we got this workflow going here. Right? Any model. I'm being as abstract as possible here. From an equation that was someplace in your book to some giant climate model you could download from a university's website someplace, is going to have the same kind of workflow. Input, execution of the model, understanding the output. All of them are key steps. All of them you have to know what you're doing. All of them you have to be aware of the errors. All of them you have to be aware of whether or not you're running the right model and all that good stuff. Now in the next lecture, we're going to be focusing in on a particular type of model that we haven't done much with this semester, namely a numerical weather prediction model, a type of numerical model, and which is often used in the context of wind power. But before we get there, let's answer two more questions. Question 5. Complex mathematical models of atmospheric processes take blank to run. A lot of computer power, B, a long time, C, a lot of memory, or D, all of these. Alright, make a choice from those 4 options, get a little feedback before you move on to our final question.